Good morning, everyone. My name is Sophia Cassandra Daoang, and today we will be discussing two topics, which is the special theory of relativity and the consequences of postulates of special relativity theory.
But first of all, before we proceed to our topic, I would like to introduce my members.
So let us discuss the first topic, the special theory of relativity. The special theory of relativity has two related theories, which is the special of electromagnetism and the three laws of motion. The special theory of relativity was coined and developed by Albert Einstein, and it is created in 1905 as an answer sa long-debated conflict between James Clerk Maxwell, the theory of electromagnetism, and Isaac Newton, the three laws of motion.
As you can see, space and time are relative. They depend on the motion of the observer who measures them, and light is more fundamental than either. This is the basis of Einstein's theory of special relativity. Special refers to the restriction to uniform motion, while relativity refers to the space and time are relative. The special theory of relativity, or special relativity for short, is a scientific theory of the relationship between space and time. This theory explains how speed affects mass, time, and space. It also includes a way for the speed of light to define the relationship between energy and matter. Do you guys know that special relativity is one of the most important papers ever published in the field of physics? And based on Albert Einstein's special theory, that the faster you go, the slower time passes. So a very fast spaceship is a time machine to the future. Let us discuss the two related theory. The Newtonian, or also known as a classical mechanics that tells the measured speed of light should depend on the motion of the observer, and Maxwell electromagnetic theory that tells the value of the speed of light is constant. Let us discuss the two related theory. The Newtonian, or also known as a classical mechanics that tells the measured speed of light should depend on the motion of the observer, and Maxwell electromagnetic theory that tells the value of the speed of light is constant.
Good morning, ABUEVA. I'm Justin Matalino, and today we are going to tackle the Newtonian mechanics. So before we start, what is Newtonian mechanics? So Newtonian mechanics is based on application of Newton's law of motion, which assumes that the concept of distance, time, and mass are absolute. That is, motion is an inertial frame. So how does this mechanic of Newton's important? So while Newton's theory of mechanics motivate philosophical ideas about matter and motion, space, time, and causality, and philosophical debates about them, its philosophical significance goes deeper. The theory is a reminder of what conceptual analysis in the foundation of physics might aspire to. So I prepare a video lesson for you guys to gain a deeper understanding of the lesson.
Today we will get started with the first general category of physics, namely Newtonian mechanics or classical mechanics. Both names are used. In general, classical mechanics might be more appropriate because Newton didn't have something directly to do with much of this category, but more like help making the foundation for classical mechanics. As discussed in the introduction of the channel, Newtonian mechanics is used to describe objects which move relatively slow, meaning less than 10% of the speed of light. Furthermore, the applicable scale is everything bigger than atoms, not including atoms. Of course, it depends on what you look at if the quantum effects become too large. So, the exact region of applicability is not completely clear. At cosmological scales, the Newtonian mechanics may also start to give you significant errors. It should be clear from this that for most real-life applications, Newtonian mechanics is sufficient for many things. In this video, we will start focusing on Newton's three laws of motion. They are probably the most well-known of his equations. You will definitely encounter them in school or high school, and then go into more advanced application at university level. So without further ado, let's discuss Newton's first law of motion, which states that the net sum of forces acting on a massive object is zero. the velocity of the object is therefore constant. Thus, in other words, if an object is at rest and you do not act on the object with any force, then the object will remain at rest. Likewise, if an object is moving with a given velocity, then the object will keep moving with the same velocity unless you act upon the object by another force. In other words, an object will keep doing what it's doing if it's not acted upon by a force. To appreciate this law, which is also known as the law of inertia, let's consider a simple example with a force diagram. Consider a box on a surface. The box is not moving, thus it satisfies Newton's first law. And if we don't act on the box with any force, then the box will not move. But notice that just because the net force is zero does not mean that there are no forces acting on the box. There are two main forces acting on the box. One is the gravitational force acting downwards to push it down. But the box is solid and it does not want to be deformed by this force, and neither does the surface allow the box to pass through the surface. Instead, the surface exerts an upward force called the normal force, which cancels out the gravitational force, and thus the net force is zero and the box remains at rest. Let's consider another case with a different example. Consider an observer which sees a car driving on the road with a velocity of 40 km per hour, and we neglect any air resistance or frictional forces. Now let's draw a force diagram of this case. The car experiences a gravitational force pushing the car downwards, but the normal force cancels out this, just like in the previous case. But now the car is also moving with a velocity of 40 km per hour forward. The car will thus continue to move forward with this velocity. Now if we were sitting in the car, we would experience that the car was stationary, which Newton's first law describes what we call an inertial frame of reference. Hence, the frame where the object is at rest, but at rest does not necessarily mean not moving. This is all relative. This is a very important point, because in principle we are moving with a great speed around the cosmos, with forces acting from many places, but we don't feel it, because just like the car, we are in a rest frame where the net force is zero. Alternatively, if you are accelerating, then you feel a force and you're not in a rest frame. Now we move on to Newton's second law of motion, which is arguably the most famous one, F equal to ma. Here the force is not equal to zero, but to the mass and acceleration of the object. Thus, to move an object with mass m and acceleration a force F is applied to the object. Before going any further, let's just appreciate this equation. We see from this equation that the mass in this case acts as a resistance to accelerate. Thus, the heavier the object, the greater the force is needed to accelerate. In this case, m is therefore called the inertial mass. If we consider the gravitational force acting on an object, we can write it as the force F equal to mg, where g is the acceleration due to gravity. Now in this case, m is the gravitational mass, which in principle does not have to be the same as the inertial mass from Newton's second law. Many experiments have been done to show that the accelerations of falling objects is the same regardless of the mass, thus leading to one of the key concepts of general relativity called the weak equivalence principle, which states that the inertial and gravitational mass are the same indeed. This is convenient because if you have to go to the bathroom scale, you will measure the gravitational mass, and then using Newton's second law would be much harder if it wasn't the same as the inertial mass. Clearly, in order to have a dynamical world, we would need acceleration. If you want a door to open, you would need to apply force to do so. For this example, let's consider the change in velocity, hence the acceleration of the trivial task of opening and closing a door. The door is initially at rest until you apply force for some time t1, which accelerates the door from a velocity of 0 to some non-zero velocity. Then you stop applying the force and the door keeps opening until you then decelerate the door for some time t2 in order to stop the door from opening by applying a force in the opposite direction, and the door will then be at rest again. Of course, in a more realistic case, your door hinges exert a frictional force that also slows down the door, but the idea should be clear. Finally, let's consider Newton's third law of motion, which states that if an object A exerts a force on object B, then object B simultaneously exerts a force on A with the same magnitude but in opposite direction. Thus we write it as as Fa in force A is equal to minus Fb in force B. So the minus sign indicates the force exerted by object B is in the opposite direction of A. Thus the third law states that all forces are interactions between bodies. Many think that rocket science is complicated, but in principle it's just Newton's third law. The problem of rocket science sadly is not the basic physical concept, but the issue of how to create and control a rocket. Nevertheless, let's consider how Newton's third law powers rockets into space. If we consider a space rocket, it has a rocket engine that ignites some rocket fuel. This process yields a huge force that pushes the rocket upwards. The spacecraft likewise exerts an equal but opposite force on the exhaust gases of the rocket. Thus the rocket's exhaust gas is pushed towards Earth by the force of the rocket, and the rocket is sent to space by the force from the exhaust gas.
Hello everyone! Ayan, ako po si Jervin Ronquillo from Group 9. Ngayon ay alamin nga po natin kung ano nga po ba ang Maxwell electromagnetic theory of light. Light is a wave of electric and magnetic fields that travels through space at the speed of light. Light is a propagating wave of electric and magnetic field. The theory describes the interaction between the electric field and magnetic field. Direction of both of the field is perpendicular to each other. Ayan, kung makikita naman natin sa presentation namin, may apat siyang ibig sabihin or part ng Maxwell electromagnetic theory of light. Narito ang electric field, magnetic field, wavelength at direction. Kung makikita nyo, nandyan din yung mga definition niya at hindi ko nasasabihin dahil may nakikita nyo naman po at ang pinaka-point na lang natin dito ay explanation ko. So, in since Maxwell theory states that light is a self-propagating wave of electromagnetic and magnetic fields that travel together at the speed of light, this theory successfully unified the previously separated concept of electricity, our understanding, and had a profound impact on our understanding of light and other electromagnetic phenomena. Ayan, at kung makikita naman natin sa presentation namin, nandyan yung example na yung picture para mas madali nyo pong makita at mas malinawan po kayo sa mga sinabi ko. Ayan lang po. Thank you po.
My name is Justine, Castillo, and i-discuss ko for today is conflict. The conflict often arise between the special territory of relative and classical Newtonian physics due to their different understanding of space, time, and motion. Neutron physics operate, understand to assume assumptions to absolute space and time. There, while special territory of relative posits the space and time are the neutronon into the single alternative called space-time, and they are relative different depending on an observes frame and difference. This conflict becomes particular appreciate and every high speed or the presence of strong gravity fields are the predictant of the each territory, diversity, and significantly. Thank you.
ABUEVA. I am Justine Tolentino again, and in this video we're going to tackle the Albert Einstein theory of special relativity. So, Albert Einstein on 1905 theory of special relativity is a crucial paper in physics, explaining how speed affects mass, time, and space, defines the relationship between energy and matter by allowing small amount of mass to be interchangeable with enormous amounts of energy. This theory is used in special cases such as huge energies, ultra-fast speeds, and astronomically distances without the complications of gravity. Einstein officially added gravity to his theories in 1950s with the publication of his papers on general relativity. As an object approaches the speed of light, its mass becomes infinite and the energy required to move it becomes insufficient. These cosmic speed limits inspire new physics and science fictions. So I already prepared another video lesson for you guys to gain a deeper understanding of this lesson.
Time. You can't see it, you can't hear it, you can't weigh it, but we experience it every moment. The whole piece of time is a landscape, and we move through it, slice by slice. But do we really understand time? Is time same for everyone? To understand time, let's go back in time and make a small journey with a certain young patent clerk, Albert Einstein. Imagine you're traveling with Einstein in a train moving at a certain uniform speed. The train, relative to the outside environment, is in motion. The two of you sitting inside, on the other hand, observe each other as stationary objects, as both you and the train are moving at the same speed. Hence, relative to the train, you are stationary, and the laws of physics stay same inside the train as they would on the ground when you are standing still. Now, let's consider you get off the train and observe it moving across in front of you. Now, you are stationary, and relative to you, Einstein is moving with the same speed as the train. This is the phenomenon of relative motion, and we observe it every day. Does everything in the universe observe this relative motion the same way? Yes, everything except light. Light behaves in a different way. Imagine you have a light clock with you. This light clock has two mirrors in the opposite directions and a light beam bouncing between them. Now, let's say the distance between the two mirrors is d, and the time for the light to cover that distance is t. For the sake of simplicity, let's say it's 1 second. So, when this clock is with you at rest position, the light bounces between the mirrors, covering distance d in 1 second, which gives us the speed of light s. Now remember, speed is distance per unit time. Now consider Einstein also possesses the same light clock with him. Only this time, he's traveling in a spaceship along with the clock. When Einstein travels in a certain speed, the clock travels with the same speed of the spaceship in the same direction. Here, light has to travel an extra distance in the same 1 second. Let's consider this distance to be capital D and represent the speed of light here as capital S, which has to be greater than small s. But something's wrong here. Because in the late 1800s, the Michelson-Morley experiment tried to detect the relative motion of the matter through an ether and concluded that the speed of light is constant. This cosmic speed limit is known as c. So in our little scenario, small s and capital S are equal. So for the speed of light for both you and Einstein to remain constant, something has to give way. That something is time. It turns out, time slows down when you travel faster and faster, nearing the speed of light. So the faster Einstein travels, slower the time passes for him. Hence, what could be a day for Einstein in space could be as much as 50 years for you on the ground. This became the fundamental conclusion of the theory of relativity. a theory proposed by Albert Einstein in 1905. This theory broke the traditional understanding of time as a constant entity and proved that time, in fact, is different for different observers. The theory of relativity led to many other invaluable findings, the most famous of which is the equation E equals mc squared. But more on that later.
Since special relativity showed us that the space and time are not independent of one another, but can be mixed into each other, and therefore it must be considered as the same object, which we shall denote as space-time. Now let's proceed discussing the consequences of the postulates of special relativity theory, known as space-time mixing, the relativity of simultaneity, time dilation, length contraction, mass energy equivalence, and cosmic speed limit.
Hey everyone, our second topic is the consequence of the postulate of special relativity of theory. But before that, I'd like to introduce myself. I'm Athena Joyce Mondala, but you can call me AJ for short. So let's go with our...
Hi. So you want a simple guide to the theory of relativity? Great, you've come to the right place. Part 1. Classical relativity. Let's start with some absolutes that we need to accept. 1. There is no such thing as absolute motion or absolute rest. Objects move relative to each other. For example, look at the truck with two kids playing catch. The truck is moving at a constant speed of 50 miles per hour, but as the kids are also moving with it at 50 miles per hour, they could easily think that they are standing still. When the children throw the ball at 10 miles per hour, they observe that the ball they have thrown is moving at 10 miles per hour. But their little brother, who is not on the truck and is standing still, has observed that the ball has moved at 60 miles per hour. He has added both the speed of the truck and the speed of the ball together. But is the little brother really standing still? No. The Earth is constantly in motion, the Sun is constantly in motion, and the galaxy is constantly in motion. Therefore, nothing is ever at absolute rest or absolute motion. Things just move relative to each other. This is classical relativity. Part 2. Special theory of relativity, time dilation. The second thing we need to accept is that the speed of light is the same for all observers. So, let's imagine a beam of light being reflected between two mirrors. Let's replicate this setup so we have another beam of light being reflected between another set of mirrors, but this time the mirrors are moving close to the speed of light. We can see in the moving set of mirrors that the beam of light is moving a greater distance. Now, let's put a couple of people into this scenario. Meet Alex. He sits inside the moving set of mirrors, and Bill sits inside the stationary set of mirrors. The speed of light must be the same for both Alex and Bill, and their light beams must hit the bottom mirror after the same amount of time has passed. But, as Alex's light beam is covering a longer distance, how is that possible? Well, the only way for that to work is if time for Alex slows down. Look at the clock hand. Notice how Alex's clock hand is moving much more slowly compared to Bill's. Time for Alex has slowed, which allows his light beam to travel a greater distance. Look at it this way. Speed equals distance divided by time. As Alex's distance is more, the value of his time must be more, or rather Alex's 1 minute actually turns out to be longer than Bill's 1 minute when you compare the two. Time has slowed down for Alex. This is called time dilation. This is quite a hard concept to grasp because it seems to go against what we experience on a practical level. But to understand the theory of relativity, you must stop thinking of time as a fixed unit for everyone. Time is relative. Confused? Don't worry if you don't grasp all of this immediately. Remember, it was the most brilliant scientist of the 20th century who put forward this theory, so feel free to rewatch this part of the video as many times as you need. Part 3. Special theory of relativity. Length contraction. In the previous section, we spoke about how the speed of light remains the same for Alex and Bill because while the distance Alex's light beam travels is more, his time has dilated. However, distance and time don't increase by the exact same amount. In fact, time doesn't actually dilate enough to account for the speed to remain the same for both boys. Something else happens: length contraction. When objects are moving close to the speed of light, not only does time slow down, but the object itself contracts. This is called length contraction. So in this scenario, Alex and his mirrors are actually smaller than we thought, and therefore the distance the light beam has to travel is actually smaller than we thought also. In conclusion, time dilation and length contraction work together to ensure that the speed of light remains the same for both Alex and Bill. Einstein preferred to think of space and time not as two separate things, but one entity. He called it space-time. Part 4. Time travel. Time slows down for objects travelling close to the speed of light, and time stops altogether for objects travelling at the speed of light. It then follows that time must go backwards if objects travel faster than the speed of light. So far, it has been seen that no object can travel at the speed of light. On approaching the speed of light, objects start to increase in mass rather than speed, and it would take an infinite amount of energy for an object to achieve the speed of light. This is why we cannot travel back in time. We simply have not been able to reach a greater speed than the speed of light. Part 5. General Theory of Relativity. Einstein realized that the special theory of relativity, which we explained previously, only worked for circumstances when things moved at constant speeds through the universe. What about when objects sped up? What about the effect of gravity? And come to think of it, what is gravitational pull after all? Einstein theorized that objects warped space-time around it, causing it to become curved, and as a result, objects experienced gravitational attraction to each other. This warping of space-time explains how objects behave as they move through space. This is the general theory of relativity. Part 6. How do we know it's true? How do we know that the theory of relativity is true? Well, countless experiments have been carried out, and Einstein's equations hold true. Modern GPS uses Einstein's theory of relativity to pinpoint our locations with impressive accuracy. In 1971, an experiment was conducted with 4 super-accurate atomic clocks, which were set to the exact same time as a reference clock. The clocks were placed aboard commercial flights, and the planes flew twice around the world, first eastward and then westward. When the clocks returned and were compared to the reference clock, the clocks were no longer all synchronized, and the differences were consistent with the predictions of special and general relativity. So, that concludes our explanation of the theory of relativity. Bear in mind this is a very simplified explanation, but it should give you a basic understanding of the core ideas so you can study further on your own. We hope you enjoyed this video, and be sure to subscribe to London City Girl to see other interesting videos.
Muli, ako si Jervin Ronquillo at alamin naman natin ang relativity of simultaneity. The relativity of simultaneity is a concept in special relativity theory which says that if two events are separated in space or position, it is absolutely impossible for the two events to occur simultaneously for two observers. This is the principle of the relativity of simultaneity. An event is only simultaneous for an observer but not necessarily simultaneously for another observer. The relativity of simultaneity is the idea that whether two spatially separated events happen at the same time is not absolute but depends on the observer's reference frame. So, the time it takes to reach the light of event 2 will be short relative to observer B outside the train. Ayan kung makikita natin sa presentation namin yung picture, yan yung example. Kung makikita natin, magkaiba sila. Kung makikita natin sa unang picture, may kaganapan na magkakahiwalay sila. Kung pareha sila ng layo.
Second topic is time dilation. The time dilation is the phenomenon predicted by Justine, special theory. For our relative, it is the states time that pass differently for object movement relative to each other. Essential time slow down for objects in motion, and compared to those to rest, this is the effect becomes more produced by the speed of object approach the speed of light.
So let's go with number 3, which is light construction. When discussing light construction in the context of postulate of special relativity, you can explain that according to Einstein's theory, objects in motion appear shorter along the direction of their motion when measured by an observer at rest relative to the object. This phenomenon occurs as a consequence of the realistic effect of dilation and space construction, which becomes significant at speed approaching the speed of light. It's a fundamental concept that challenges classical motion of space and time, with practical implications for fields such as particle physics and astronomy.
Next is mass-energy equivalence. Mass-energy equivalence is simply about special relativity Einstein equation, which is the E equals mc raised to 2 that signifies that mass and energy interchangeable. Same as I mentioned earlier sa first topic namin about space and time are not independent to each other but can be mixed together and considered as same object, so-called space-time. That includes a way for the speed of light to define the relationship between energy and matter. So what is mass-energy equivalence all about? Mass-energy equivalence entails that the total mass of a system may change, although the total energy and momentum remain constant. For example, the collision of an electron and protons annihilates the mass of both particles, but creates energy in the form of photons. The mass-energy equivalence combined with the weak equivalence principle results in the prediction that all forms of energy contribute to the gravitational field generated by an object. Let's proceed to the last consequences of the postulates of special relativity, the cosmic speed limit. It is a fundamental principle that governs the universe. The cosmic speed limit refers to the maximum speed at which information or matter can travel through the universe. This limit defined by the speed of light in vacuum, which is approximately 299,792,458 kilometers per second. The concept of a cosmic speed limit is a cornerstone of Albert Einstein's theory of relativity. It challenges our everyday experiences and institutions, as it suggests that the laws of physics are the same for all observers, and regardless for their relative motion. As you can see in our first picture, it measures the building height in degrees of the apparent angular height visible from the fixed distance c. Almost additive for the small heights. Two buildings measuring 1 degrees. Each would stack up to 1.9994 degrees, almost exactly 2 degrees, while the second given picture is taller buildings. Height is no longer additive. Two buildings measuring 45 degrees, each would stack up to 63.4 degrees, not 90 degrees. Also, the degrees-based scale of the height is limited with the unreachable maximum height of 90 degrees. The right measure of height is not degrees. It's c tan degrees, and it's additive and unlimited. The concept of the cosmic speed limit is more than just a speedometer for the universe. It's a window into understanding the fundamental laws that govern reality. By exploring this limit, we delve into the heart of physics, uncovering the mysteries of the time, space, and the universe itself. That's the end of our discussion about special relativity and the consequences of the postulates of special relativity.